Okay, so let's start with representing positions. What I've done is I've shown two coordinate frames. Let me call this frame the origin as OO, XO, YO, and the other one as O1, X1, Y1. And let's put a random point on, let's put it, let's say here. Okay, so this is a point in space, and you can represent that point in multiple ways. Because I have two frames, I can define at least in two ways. So what I'm going to do is I'm going to draw a vector or a line from the origin to P. I can also use a line from the origin OO to define it. So depending on how I represent it, I can have different notations. So let me call this P1 because I'm representing it using the frame O1. I can also write it as PO to represent it with respect to frame 0. So if I want to find the coordinates of, let me write a few things down before I say that. So P is a random point in the plane, and then OO, XO, Y0, and O1, X1, Y1 are two coordinate frames. Okay, so P can be represented in two ways. One is I would write it as P0. So that is trying to write the coordinates of P by using this origin. Okay, so if you count here, this is 1, 2, 3, 4, 5, 6, 7. Looks like it's 7, and 1, 2, 3, 4, 5. So it looks like the coordinates of point P are 7 for the X and 5 for the Y. You could also write P with respect to coordinate frame 1. So this is using this. So 1, 2, 3, that's 3, 1, 2. So 3 for X, 2 for Y. So the notation which we'll be using is, if you want to find the coordinates of a point in frame 0, it will be P0, frame 1, P1. Okay. So it's just two ways of, P is the same variable, right? It's represented two ways, similar to apple is an apple. You can call it apple in English or apple in Spanish. It will be the same apple. So you could also write coordinates of the origin. So O1 is the origin. I want to find the origin in frame 0, so in this frame. So for that I need the coordinates of this point, which is 1, 2, 3, 4, and then 1, 2, 3. So O1 as seen from frame 0 is going to be X is 4, Y is 3. You could also find the coordinates of frame 0 from frame 1. So for that, if I want to really go backwards in the left side, then this will be -4, right? It is the distance of point 0 on the x-axis. The x-axis correspond to x1 is -4, and for the y-axis I need to go down, which is again minus, so -3. Okay, so again that's the notation. That's O1 is a point. Okay, 0 is the frame, similar to that frame. O0 is the point, and 1 is the frame with respect to which I wrote down its coordinates. Okay, and this will be used again and again, where we'll be keeping track of frames. When we look at manipulators, there are different links. We'll always be looking at the coordinates of the manipulator with respect to, say, the base. We may also look at the coordinates, the end effector or the pen with respect to the ground, and so it's always good to keep track of points in multiple frames so that we can then use, let's say it is a camera over here, then you to find its coordinate with respect to the camera which is in the ground. You might want to plan the motion with respect to the shoulder and so on. Okay, so that's positions. These are only translations. Let's look at rotations. So what I did was O0 x1, sorry, O0 x0, y0 is my original coordinate frame. I rotated the coordinate frame, but keep the origin fixed. So O1 is the new coordinate frame, the rotated coordinate frame. X1 is the new x-axis, y1 is the new y-axis. And what I'm trying to do is I'm trying to represent what will happen to a point. Let's say this point. Let's start with this point. And when you rotate it, it will actually move there. And if there's a point over here, it moves. Okay. Specifically, this point is going to be at a unit length. Okay, and at this point is also at a unit length. So I'm going to try to figure out what happens to that point when you rotate the axis. Okay, so again, original frame is OOXOYO, and the rotated frame is O1X1 Y1. Okay, and our convention is always going to be when you turn things counterclockwise, the sign is positive, and clockwise negative. So theta is counterclockwise and is positive. Okay, so we want to find the rotation. Okay, R is the rotation matrix R1 with respect to frame O. I call it R1O because I'm looking at coordinates of this point, which is in frame 1, but I need to find its position with respect to frame 0. Same convention as before. Whatever frame you want to represent always goes on top. That always represents with respect to which frame you're trying to look at the rotations. So that would be 2 points. This point, which I'll call x10, and then y10. I don't need this line. This line just shows that this is going to be a 2 by 1. I'll write the x and y position of this point, and then x and y of y1, which is. So for that, I need to do a little bit of trig. I need to find the coordinates of this point. Okay, since I'm trying to find what is this point in frame 0, that's why I drew perpendiculars to frame 0. So that angle. So since this is unit length, when you rotate things, the length does not change, right? So this is still unit length, and so this is the perpendicular is going to be sine of theta, and this distance is cosine of theta. Similarly, I'll draw perpendiculars from this point to the axis y, and similar to that, I can write the distance or the position of y1 with respect to frame 0 as sine theta cos theta. Okay, so now what I can do is I can try to write the coordinates of this point Okay, the coordinates of that point are going to be, well, the x coordinate is cosine theta. The y coordinate is sine theta. Sorry, it's positive sine theta, right? Because the point, because this point is in the positive coordinates, or the positive quadrant x1. Its coordinates are positive. Cosine theta is positive, sine theta is positive. Let's say the coordinates of this point now. The x coordinate is this, but we see that the point y1 is in the second quadrant, so on the left side. So x coordinate is negative sine theta, and the y coordinate is cosine theta. That's along the positive y-axis. So it's positive cosine theta. So with that, I can now write this x10 is that point, x10 cosine theta sine theta, and then y10 is that, so minus sine theta cosine theta. So that is the rotation matrix. It basically tells you the rotation of one coordinate frame with respect to another one. So this is key. This will come again and again. The rotation of frame 1 with respect to 0 is something which should be used again and again in this course. Now, this is showing what happens when you turn x0, and how is that frame 1 related to frame 0. You could have the reverse question, which is you rotated 1, but what is the coordinates of this point with respect to frame 1. So instead of saying r1 with respect to 0, the question is what is r0 with respect to 1. And for that you do a similar constructions. The construction is, I drew the same figure essentially, but instead of dropping perpendiculars to the x0 and y0 from x1, y1, I would drop perpendiculars from x0 and y0 to x1, y1. So what that means is would drop perpendiculars this way. Okay, so this is still x0. x1 would be here, right? And then y0, y1. And I'm going to try to find the distances on this axis now. So cosine theta, I'll go a little fast on this, sine theta, so that's this distance. And then sine theta, cosine theta. And so the coordinates of this point now, earlier we wrote the coordinates of x1 because I was trying to find how x1 is looks in frame 0. Now I'm going to find x0 in frame 1. So that would be cosine theta for the x. And then for sine, we can see that that is along the negative y-axis. So it's going to be negative because this is positive and that's negative. So this is the coordinate of x0 in frame 1. Similarly, we can write coordinates of this point. So the x coordinate is along the x-axis, the x1 axis, so that's sine theta, and the y coordinate is along this, that's also positive, and that is y0 in frame 1. So if I want to write the reverse, which is r0 in frame 1, I would write x01, y01, which is just right from here, cosine theta minus sine theta sine Okay, so that's R10. This is R0. So this is R1. I'll call it R10 indicates R1 is the it's with respect to frame 0 and R01. If you look at R10 and R01, let me copy paste this. What you can see is R10 is actually the transpose of R01 transpose is R10. Okay, and this is always true. Rij is always equal to Rji with the transpose. This is the generalized form for the rotation matrix. It's very useful because now you don't have to do this math all the time. You just find one of them and just take the transpose to find how the reverse transformation works. There's another thing about rotation matrices, which is in this one you can check Ri0 inverse is always equal to R10 transpose. In fact, the property of rotation matrix is that R transpose R is always I. Okay, using this you can get. Do you know what this is called? It's probably learned this before. Is it called the identity? No, it's identity, but this is called as orthogonal matrix, I think. I think this is a standard form for what is known as the orthogonal matrices. Is that right? I forget, but this is a consequence of that identity for rotation matrix is that R10 inverse equals the transpose. So this is really good news because it's sometimes very hard to get write the inverse, and by just taking the transpose you can get the inverse. So it's really useful identity to remember. So let me circle that. Let me write a generic form. The generic form is Rij inverse is equal to Rij transpose, always true. This is generalized. Okay, so now for this course we will look at three-dimensional matrices. We stop at 3 dimensions. 3 dimensions is, so what I showed you actually is actually a 3-dimension. It's a 3-dimension rotation. Let me go back and backtrack and tell you why it's 3-dimension. Where you're saying that something rotates, it's rotating about an axis. The axis is pointing that way. So when I have the axis, it's rotating. The rotation is about the z-axis. So the standard form for writing a 3x3 matrix is when you have rotation about the z-axis is you got to just append 1, 0, 0, 1. I'll just write it down. So what I have shown is in fact a 3-dimension rotation. So I'm going to write down 3D rotations. All the rotations are 3D, at least in this course. So R10, what I wrote down is actually this: cosine theta minus sine theta. Okay, so this indicates rotation about z-axis. In other words, the third row and the third column, you'll have 0, 0, 1 because the vector in the z direction does not change. It just remains as it is. So that is so what I showed you was actually a 3-dimensional rotation. Now I'm going to write down rotations for x, y, and z. So this is rotation about z. You could write rotation about x and rotation about y. And those are the things which we'll be using throughout this course. So let me write it down. What I will do is, and this is will happen throughout the course, is instead of writing cosine theta minus sine theta, it's a lot of work. I'm going to abbreviate cosine theta as c theta. If it was phi, it would be cosine phi, would be c phi, and so on. So I'm going to write all 3D rotations and I'll let you go. This is the last thing for today. So all 3D rotations. Okay. The notation we'll be using is r, x, theta, which indicates that this is rotation about the x-axis by an angle theta, and theta is counterclockwise. So let me write z first, because that's the one I wrote down. So that will be c theta minus s theta 0, s theta c theta 0, 0, 0, 1, where s theta is sine of theta, c theta is cosine of theta. Okay. Similarly, I can write rotation about the x-axis. When you have rotation over the x-axis, there will be a 1 for the first row, first column. 0, 0, 0. Cosine theta minus sine theta. 0, sine theta, cosine theta. And then rotation about the y-axis. So that would be c theta 0, s theta 0, 1, 0 minus s theta 0, c theta. Okay, if you want to derive this, you're going to do the same derivation I did for the rotation about the z-axis, and you have to change it from rotation about z, you'll change it to rotation about x, and so on. So this thing is the most important thing. The only thing which I think is tricky is that there's a negative sign here. You would expect it to be a negative over there, like those two. Hold on. I think I did a mistake. This is wrong. This should be here. Okay, so it looks, so that one and this one looks similar in the sense there's a negative there, but this one looks slightly off, but that is actually the right formula. Okay, so I'll stop a little early today. I'll see you. I'm not here on Thursday, so I will post a bonus homework for you to do, and then we'll meet on next Tuesday, and I'll put down the homework, and if you want extra time, the due date is Tuesday, next Tuesday, but if you want more time, just let me know.